and Bikas, Professor Guido Knapp, and participants of this workshop. On behalf of the ICR, Indian Agricultural Statistics Research Institute family, I welcome you all to this online workshop on statistical meta-analysis. This workshop is being co-chaired by highly reputed, internationally recognized twin brothers, statisticians, Professor Bimal Sinha and Professor Bikas Sinha. And speaker for the workshop is Professor Guido Knapp. Let me begin with just one slide for IASRI. It is a premier institute of relevance in statistical sciences. When I say statistical sciences, it is statistics, computer application, and bioinformatics, and their judicious fusion in agricultural sciences for enriching quality agriculture research and informed policy decision making. Just to share with the participants that we are in 10th decade in the service of the nation. We started in 1930 as statistical section in then Imperial Council of Agriculture Research. Therefore, 92 years in agricultural statistics. 1965, there is installation of ICR's first computing facility, IBM 1620 data processing system. Therefore, 57 years in computer applications. 2010, we established the National Agricultural Bioinformatics Grid. Therefore, 12 years in agricultural bioinformatics. We shall be completing 100 years in 1929 and preparing programs for celebration 100 years from now. We had been serving three different systems: National Agriculture Research, Education, and Extension System. When I call this National Agriculture Research, Education, and Extension System, this includes 113 ICR institutes, 74 agricultural universities, and 727 Krishi Vigyan Kendras. National Agricultural Statistics System, this is basically government system where data is being collected on the different aspects of the agricultural statistics. And we are also having e-governance activities of ICR and simultaneously have to prove ourselves to our peers on basic research in statistical sciences. We had been conducting MSc and PhD in agricultural statistics, computer applications, and bioinformatics, and conducting several of the customized training programs. Our mission is to undertake research, education, and training in agricultural statistics, computer application, and bioinformatics for agriculture research. And these are two broad mandate of the institute: research, education, and training in agricultural statistics, computer application in agriculture and agricultural bioinformatics, advisory, consultancy services, methodological support, computational solutions to National Agriculture Research and Education System and National Agricultural Statistics System. The institute has made tremendous contribution towards agriculture research and agricultural sciences and agricultural policy planning. I will not be going through that I will leave for some other day. And I have a very pleasant duty to introduce the co-chairs, Professor Bimal Sinha and Professor Bikas Sinha. Professor Bimal Sinha is at present professor at Department of Mathematics and Statistics, University of Maryland, Baltimore County in USA. Professor Bimal Sinha, popularly known as Bimal Da, and Professor Bikas Sinha, popularly known as Bikas Da, both were born on 16th March 1946 in village Atgaria, district Pabna in Bengal province of undivided India, now in Bangladesh. Professor Bimal Sinha and Professor Bikas Sinha both did their PhD in statistics from Calcutta University. Professor Bimal Sinha had been faculty at Indian Statistical Institute, Kolkata during 1971-74 and 77-80. He has been a faculty, a colleague of Professor C.R. Rao at University of Pittsburgh during 1980 and 85. He is the founder of Statistics Graduate Program and Professor University of Maryland, Baltimore County since 1985, and Presidential Research Professor, if I remember, it is 2008. University System of Maryland Board of Regents Research Professor. Based on his enormous contributions, he has been elected Fellow of American Statistical Association, Fellow of Institute of Mathematical Statistics, Research Mathematical Statistician, U.S. Census Bureau, Chief Statistical Advisor to Barry Nussbaum, Chief Statistician at United States Environmental Program for more than 20 years. He has, to his credit, more than 150 original research papers. He has been mentor of 30 PhD students, direct his students, but if I say indirect students, they will be their count will be very difficult to do. His research area of interest include multivariate interest analysis, asymptotic theory, rank set sampling, statistical meta-analysis, data analysis under confidentiality protection. His research contribution in the area of environmental statistics has been recognized through a Distinguished Achievement Award from the Environmental Statistics section of American Statistical Association. He received the University System of Maryland Board of Regents Excellence in Research Award in 2012. Professor Sinha has served on editorial board of several national and international statistical journals. He had been plenary keynote speaker at numerous international conferences. On behalf of the participants and on behalf of Indian Agricultural Statistics Research Institute, Professor Bimal Sinha, we professionally welcome you, hearty welcome you to this workshop on statistical meta-analysis.
Thank you. Thank you.
These are some of his books. There are many. I could not find photo for all, but I could lay hands on my three. One is directly related with today's topic, statistical meta-analysis with applications. Another is rank set sampling. Third one is frontiers in probability and statistical sciences. Professor Bikas Da, our Bikas Da, which we always call him. He has done his PhD in 1972 from Calcutta University, Calcutta, India. He had been assistant professor of statistics during 1972-75 at Calcutta University, visiting as associate professor, Institute of Mathematics, Federal University of Bahia, Brazil, 1975-79, associate professor of statistics at Indian Statistical Institute, 1979, professor of statistics, Indian Statistical Institute from 1985, from where he superannuated. He had served a very prestigious position as member, chairman of National Statistical Commission to the Government of India. He has widely traveled on academic assignments, including Brazil, USA, Baltimore County, Germany, Canada, Finland, and Thailand. He has been on UN expert on mission at a workshop in survey methodology for post-enumeration surveys in Guinea-Bissau. He has been consultant to US EPA. He has several editorial assignments, which include associate editor of Journal of Statistical Planning and Inference, editorial board member of Sankhya, Calcutta Statistical Association Bulletin, and editorial member of Pakistan Journal of Statistics. His major research include inference, including finite population inference, optimal design of experiments, sequential estimation, statistical models and methods in sociological studies, characterization problems, reliability-related inference, environmental statistics. He has several honors and awards to his credit, which includes PC Malanobis Medal, elected member of International Statistical Institute, coveted plaque awarded by Forum for Interdisciplinary Mathematics, President Section of Statistics, Indian Science Congress, Centenary Medal of Excellence by School of Tropical Medicine, Calcutta. He has a very impressive list of collaborators across the globe, more than 110 by now. This is a old information, 105. More than 160 original research papers to his publication, 7 books, research monographs on models for social networks with statistical application, optimal covariate design theory and application, design and inference in finite population sampling, statistical methods in social science research, topics in optimal design, theory of optimal design, and optimal mixture experiments. Because the outstanding researcher, teacher, motivator, and inspiration for all of young colleagues. Special attachments to ICAR-IASRI. Thank you, Bikas Da, for being us on this occasion. We heartily welcome you to this workshop.
Thank you, brother.
It is your idea, it is your brainchild to have this workshop in online mode.
Thank you. Thank you.
Now, I'll hand over to the co-chairs for the further conduct of the session. Professor Bimal Da.
Yeah. Okay, thank you. Thank you, Rajender Bhaiya. Thank you, Dr. Parsad. So on behalf of now UMBC, which is the statistics group here, and Dr. Guido Knapp, our today's featured speaker, is certainly a part of the STAT network at UMBC. So I welcome all of you again. And I really thank my brother and of course, Dr. Parsad also for thinking about this contemporary topic as a topic for workshop. So the statistical meta-analysis, and we cannot have a better speaker than my longtime friend, research collaborator, Dr. Guido Knapp. Any international conference in which meta-analysis is a component, Dr. Knapp is a sought-after speaker. As we are very lucky and blessed that he could afford the time, he could spare his valuable time to be with us for, of course, for a long period of time. So we should not take him for granted. It's very hard to get Dr. Knapp. He's really, you have to really play according to his schedule. It's very, very hard to get him. Anyway, so when it comes to the topic of statistical meta-analysis, I would say the internationally leading expert, world number one, is Dr. Guido Knapp. He looks very young, but he's very, very highly motivated scholar. He has been with the University of Dortmund Department of Statistics for many, many years, essentially all his life. He got his PhD in statistics in 1996 from the University of Dortmund. But unlike in Indian university and also in North American universities, in most European countries and universities, a PhD is only a stepping stone. After that, you have to go through a long, rigorous process of serious research you have to do to finally earn what is called the habilitation. And it took for Dr. Knapp about 12 years of rigorous training, going through all sorts of coursework and eventually writing another dissertation to earn the habilitation, which he earned in 2009, which is equivalent to now a full professor in North American university. She is now qualified to supervise students, which he does regularly. And when I look at the title today, the lectures on statistical meta-analysis, you have seen a copy of the book. That book is the second book on statistical meta-analysis. Our book, published by John Wiley, with the three authors, myself, Dr. Knapp, and his advisor, Professor Hartung. So this is the second book. Earlier in 1985, there was the first book on statistical meta-analysis by Ingram Olkin and Larry Hedges. Olkin from Stanford, Larry Hedges from University of Chicago. And by now, there are many books on statistical meta-analysis because the topic has been so popular. And most of the recent books, maybe all of them, they are based on applications of meta-analysis in various disciplines, you name it, all sorts of disciplines with good computer-aided software known as R. And by the way, Dr. Knapp is an expert not only in theory of meta-analysis, also in applications. And I see that Dr. Knapp selected probably 6 or 7 topics, which is so nice of him, starting with the general idea of meta-analysis, going through some details of various applications, and he included also R packages. So I think this will be very, very useful for all the participants. If you're familiar with R, if not, there's an opportunity for you to learn R also. In North America, a workshop like this will not be free. The conference or the workshop attendees, they have to pay at least $1,000 for a 3-hour workshop. It's not free. And the speaker gets some honorarium. But thanks to Guido Knapp, who has a lot of respect for Indian culture, Indian values, and Indian tradition in general, and his enormous respect for the statistical twins, he agreed to do it totally free. And I thank the Institute also for making it available to all the participants. I again thank Dr. Parsad for giving Dr. Knapp the opportunity to present to showcase his whatever he wants to do. And it's really a rare and unique opportunity for all of us. Okay. So in these remarks, because if you want to add something, if not, we'll hand it over to Dr. Knapp.
See what is going on. I cannot. I have
Guido in Calcutta University Department. So he is an excellent speaker, and let us look forward to listen to him.
Okay, so
that is all yours now.
Okay, thank you very much for the kind invitation and the kind introduction to this workshop. Maybe it's a lot of program, so I can share the screen. So I call these lectures on statistical meta-analysis. Maybe we will have 2 lectures today. And the topics, I will first give a kind of introduction. Then you have to learn what are the generic meta-analysis models. Then I will briefly introduce 2 R packages for meta-analysis. And then I give you an example for meta-analysis of normal outcomes. And so my proposal is, after this 4th point, we will make a break of 10 minutes. Then I will talk about meta-analysis of binary data, and then some points which are important after doing meta-analysis. You have to ask whether there is some kind of publication bias, or when there is large heterogeneity, how to explain it. And we will discuss these points in these lectures at the end. So first of all, a little bit to the relevant R packages and the main references to these R packages. I will use the meta4 and meta package. And maybe when you use R, you know that's rather dynamic. And when I prepared my slides for this workshop, I've learned that all the data sets from meta4 are now in an own R package, metadat. So that's simply new, and all what you have to do is, of course, to go to the metadat data set when you want to learn or want to use some data sets already given from meta-analysis. So there are some books or articles for these 2 R packages, but they also have websites. And of course, there are more current versions for the references. And it's important also that you always look into the documentation in R, what's going on in the R packages. As I've already said, it's quite dynamic. And a remark, I do not know how it is in the agricultural sciences. Often I work in the area of clinical or trials, epidemiological studies. And there are also some rules how to do the meta-analysis. And there is this PRISMA statement, the preferred reporting items for systematic reviews and meta-analysis. And when you go to the website, you get all the information. And the idea here today of my workshop is that I will present you the statistical meta-analysis that is relevant for this PRISMA statement. Yeah, so a short introduction. I don't read all this text here on the slide. So meta-analysis is a relatively, let's say, young term. It's termed by Glass and Educational Researcher in 1976 as a statistical analysis of large collection of analysis results from individual studies for the purpose of integrating the findings. That's the notion meta-analysis, but we can also say combining experiments or whatever you want to do as systematic reviews. Historically, there are some old works by Pearson in the life sciences, Birch in physics, and of course, Cochrane and Yates, Tippett Fisher, especially in the agricultural sciences. And nowadays, meta-analysis is applied in a lot of areas, and I've just given here a list. Yeah, you can read life sciences, agriculture, archaeology, and so on. But the methods we use here can we also use in interlaboratory trials or metrology. So normally when you do a meta-analysis, you have 4 important stages of this research synthesis. The first one is simply the problem formulation. Of course, you have to have a problem. And you define your problem, and then you start searching for the data. Then yes, the second stage is the data collection stage. and maybe you find a lot of articles about your problem you have, and then you have to evaluate the articles and extract the data. And finally, you do the data analysis and the interpretation stage. And as a statistician, I will talk about the last stage, the data analysis and the interpretation stage. And usually what we have in meta-analysis is that we have the results from published studies. If you have original data, you can do simply mixed linear effects models, and it's a completely different story. Here we consider only results from published studies. And what is the motivation for the statistical meta-analysis? Cochrane was an epidemiologist, and there is this Cochrane group. And when you look in the handbook of the Cochrane group, there are several arguments for doing statistical meta-analysis. First of all, you want to increase the power of your analysis or to improve their precision. It's nearly the same. Maybe what you also can do with meta-analysis, you can answer questions not posed by the individual studies, so that maybe also you can combine not the primary endpoints, but also can combine now secondary endpoints. And finally is that you can try to settle controversies. Maybe that you have some studies with the positive and other studies with the negative results. Or on the other hand, also that you maybe come to the conclusion that you can generate new hypotheses, or that you simply need more information, more trials to get an answer to your question. So, and just some 3 general examples to show you simply what is the data situation we have here. My first example is an experiment of the percentage of albumin in plasma protein in human subjects. Let's say we have 4 results from 4 experiments, A, B, C, D, with the different sample sizes NI. And you simply observe the mean, let's say, of the 12 participants in experiment A, and you have an information about the variance in each of the experiments. And you see that the mean here is relatively similar. Albumin percentage is a kind of a fixed number in human subjects. But you see here, for instance, that the variance of the 4 experiments are rather different. And that's a typical problem you have. You cannot use a simple one analysis of variance with homogeneous variances. You have to consider heterogeneous variances. Another aspect is here the comparison of aspirin versus placebo in patients following a heart attack. You have maybe here 6 different studies with the number of patients and the mortality rate. So we have a binary outcome. You know the mortality rate, you know the number of patients, and then you can try to answer the question whether aspirin is better in treating the patients with following a heart attack than placebo. And the other possibility is that you have maybe estimates from a model. Usually here it's a logistic regression model where you have your odds ratio, but it's an epidemiological experiment or example. And in epidemiology, when you have rare events, even if you estimate an odds ratio, they talk about the relative risk. So we have here 19 studies. You know the number of patients, or not really patients here, a woman was exposed to environmental tobacco smoke, and you get an estimate of the relative risk with a confidence interval. And it's also a situation now that you can try to summarize the results from these 19 studies given these results. So you have seen different examples of the data situation you could have in meta-analysis. So what are the possible data now from the published studies? Only when you have a very, very, very small study, maybe you have the raw data in the article so that you can use it. Normally, you only have summary statistics. In former times, sometimes you only have a p-value or something like that, and you can do some kind of combination of p-values. I don't talk about this topic today. What I will talk about is when you have effect size estimates plus standard error, so something like a precision you have. So this is the data required for meta-analysis, especially for the 2R packages I will discuss with you. So sometimes you only have the effect size estimate plus a confidence interval, like the example on the last slide. Sometimes you have effect size estimate plus p-values, and sometimes only you have the effect size estimate plus the sample size. And depending on the effect size you use, sometimes it's sufficient that you have the idea of the confidence interval or a p-value, then you can calculate the standard error. So I will talk about the situation, what you see here in blue, effect size estimate plus standard error. And that simply means when you have a data set may be given in this form here, there is a study on the effects of teachers' expectancy on pupil IQ, that there is an effect size estimate D. It's not important exactly now what it is. It's for the standardized mean difference, an estimator called Cohen's D, and you need the standard error of this D. If you have from all the studies this information, you can do the combination, no problem. From the secondhand smoking example, where we had the relative risk and the 95% confidence interval, it's not so easy to do the meta-analysis directly because we need an information about the standard error. And it's important that you always know on which scale do we do the meta-analysis and on which scale do we do the reporting of the meta-analysis. It may be a difference. So the report here from the study is on the relative risks scale with the confidence interval. But we do the meta-analysis always on the log scale for the relative risk. So the question now is, how can we extract the standard error of the estimator? And if always, when you look at the interval, you will see that it's not symmetric about the estimate. And so, and that's a hint that the original analysis is done on the log scale. And for instance, for relative risk and odds ratio, when you have binary data, also for the ratio of means, when you have continuous data or normal data, or we'll give you an example later, the meta-analysis is done usually on the log scale. And first what you do, you log transform the estimate and the bounds of the confidence interval. So that means that assuming that a critical value from the standard normal distribution is used, so that is that you have a so-called wild confidence interval for the log relative risk. So the log relative risk plus minus the standard error times the critical value from the standard normal distribution gives you the confidence interval. So, and with these assumptions, you can compute the standard error. Because when you look at the length of the confidence interval, it's 2 times the standard error times the critical value. And then you can compute the standard error as the length of the confidence interval divided by 2 times the critical value. So, and then you have the estimate, the log relative risk, and the corresponding standard error, and you can do meta-analysis. So sometimes also it's so that is the conclusion, it is necessary to do some data pre-processing so that you can do the meta-analysis. So that is the part, the introduction part on the data. And now the two sorry, is there a question or so? Okay. So, and now we come to the two basic generic meta-analysis models. There is a little bit notation, and but that's all. I always use the theta I and the sigma square for the effect sizes and the variances. We will distinguish between two different models. That's the fixed effect model and the random effects model. And in the fixed effect model, we assume that the effect sizes are the same, and then we talk about a common effect size. Yeah, sometimes also in the medical literature, they also talk now about a common effect size. Yeah, but I will still use the notion fixed effect model when I assume a common effect size. And the other model is the random effects model. And the parameter of interest here now is called the average effect size. So let us consider the following. We have K, and that's important now, independent studies. That means that the results of all the studies you use for the meta-analysis are different. I do not know how it is in the agricultural sciences, but sometimes in epidemiology, maybe you have results after 10 years and the same study after 15 years, and then you have to decide which of the results you will use for the meta-analysis. So the important thing is that we have K independent studies. And with theta I will denote the true effect size in the ith study. And of course, from the study, you have an estimate. Yeah, so with theta I hat, I will denote the estimated effect size in the ith study. And then you need the variance of the estimator you have. And in the notation here, I will just indicate that the true variance of your estimator may also depend on the true effect size. Like in the binary case where the binomial data, maybe we have the expected value, it's n times p, the probability, and the variance is n times p times 1 minus p. So, and the important thing now is that for the true variance, you need an estimate from the study, yeah, from the publication. And then we simply assume that the estimate you have comes from a normal distribution with the effect size theta I and the variance sigma square. And you need an estimate of sigma square of theta I, namely hat sigma square hat of theta I. So I prefer this kind of notation, but after a while I will go to this shorter notation, what you find usually in the literature. But it's important that you keep in mind that this here is not an estimator of the population variance, it's an estimator of the variance of an estimator. Yeah, so the justification for the normality assumption here is maybe central limits theorem or the asymptotic normality of maximum likelihood estimator. So, and in this kind of model here, now we try to use linear mixed effects model theory for the statistical analysis. So, and we start with the fixed effect model. So the assumption is that now the effect sizes in all the studies are identical. We assume so that in study 1, it's the same effect as in study 2 and so on. And then we briefly drop the index and say that theta is a common effect size. When the fixed effect model is a true one, we simply have this kind of model here, yeah, which have the common effect size as the expected value, and to have here the variance. And note that I have already plugged in here the estimator. So that simply means that we do the analysis conditionally on the observed variance of the estimator in the studies. Yeah, and when you look at these small model here and you do maximum likelihood or best linear unbiased estimator from a linear model theory for the theta, I always use this kind of conditional because you condition on the observed variance. Yeah, so you get an estimator which is simply a weighted average of the study-specific estimates. And the weights are simply the inverse of the variances. That's all. Yeah, so in meta-analysis, we always deal here with weighted averages of the study-specific results. In the fixed effect model, the weights are simply the inverse of the study-specific variances. When you calculate then the variance of this estimator, already keep in mind that you have to have already plugged in your estimate here. The variance is 1 over the sum of the weights. And a kind of a standard approximate confidence interval based on asymptotic theory is given in this form here. You have in the middle your estimator, your fixed effects, 1 plus minus the standard error times the critical value of the standard normal distribution. So that's the classical approximate standard confidence interval in the fixed effect model. Of course, you can try to look in a statistical test whether your assumption of homogeneity is satisfied or not, that you test the null hypothesis, that you have a common effect size against the alternative that there is at least a difference between two studies. And that is usually done in meta-analysis with a very old statistics, Cochrane's Q, given in this form here, that you look at the quadratic distance between your estimate from the study and the fixed effect estimate, and you weight it with the inverse of the study-specific variances. So this statistic is approximately chi-square distributed with k-1 degrees of freedom, and you reject the null hypothesis if the test statistic is too large, larger than the critical value of a chi-square distribution with k-1 degrees of freedom. And what you want to do in some sense here is you want to prove, let's say, the null hypothesis, and you know you cannot prove the null hypothesis. And the trick a little bit here is that usually, maybe also in India, you always use 5% at the significant level, that in this situation, maybe you can use 10 or 20%. So, and recall that there is not really a assumption here exactly normal. If case you have exact normal assumption, you get, of course, exact results with the chi-square distribution. You should have keep in mind that this is a formulation for all possible effect sizes you can think of, and based maybe that the normality is based on the central limit theorem or asymptotic normality. So I could also say that here that the estimator is at least approximately normally distributed, that you have to keep in mind all the time. But what shall we do if the homogeneity assumption is not fulfilled? So I've already said that I mostly working in the area of clinical trials and combining clinical trials, the homogeneity assumption is never fulfilled because in different studies, you have different patients with different covariates like age and something like that, so that the true underlying effect size in each of the studies is different. And one possibility what you can do is that you assume a so-called normal hierarchical model. That's simply the idea you should get here. You can divide it, what I've already told you, what you observe in each of the study, you can say that this is an observational model, that the theta I is at least normally distributed with the study-specific effect theta I and the variance of this estimator here. And now you do the assumption that your expected value here in the observational model also comes from distribution, what is called a structural model, that you say that the expected value in each of the study comes from a normal distribution with an expected value theta and a variance tau square. So that's simply an assumption, hard to let's say it's just an assumption you do. The advantage of the normal approach is then when you calculate then the marginal model here, then it is that you say that your estimator you have from the study comes from a normal distribution with an expected value theta, which is now called the average effect size. And the variance you have here is now the sum of two. Yeah, so you have the precision from your estimate from the ith study, and you have the variance tau square here from the structural model. Yeah, and these parameter tau square is sometimes called the between study variability or also the heterogeneity parameter. So in contrast to the fixed effect model, where you only have to estimate the common effect size, now you have a parameter space with two variables, namely the average effect size theta and the heterogeneity parameter tau square. And the only data you have is your estimator theta I hat, and of course the information on the precision, the weight from the individual study, sigma hat square. So when you now consider these random effects model and do follow the same line as before in the fixed effects model and simply first assume that tau square is fixed, you will get the conditional maximum likelihood or conditional best linear unbiased estimator for the average effect size now for known tau square as the weighted average in this form here. And the WI's weights here are now simply 1 over the variance tau square plus sigma hat square. So the question now is, how can we estimate the heterogeneity parameter? And there are a lot of proposals in the literature, and you will see in several minutes when I discuss a little bit about the R packages. I think there are 7 or 8 possible estimators implemented. On this slide here, I've only written down one estimator, which is closely connected to the heterogeneity statistic Cochrane's QU we have already seen. And the assumption for the tau square is, when I go back, maybe, no, here, it's enough. For the tau square, that is not really a positive variance all the time. It could also be that the variance is tau square is equal to 0. That simply means that the fixed effects model is a special model of this general random effects model when you allow that tau square is equal to 0. So, and then you can calculate, for instance, these decimonial layered estimator. And so the numerator here is only of interest to explain what might be the problem here. Recall that these QC is approximately chi-square distributed statistics with expected value k minus 1. So, and that simply means that if you have a realization of your heterogeneity or Cochrane's Q statistic, which is smaller than the expected value, yeah, you have a negative value here. Yeah, and then it's a situation that you have to truncate the estimator here. Yeah, so in practice, you simply would use the maximum of 0 and the formula given here. Yeah, so, and when you have an estimate equals to 0, then the random effects model will collapse to the fixed effect model. That you have to keep in mind. So, and when you plug in then your estimate tau square here, so that's simply a change in the notation, then I now have W hat I's, yeah, so kind of estimated weights. Yeah. So, and when you do a classical variance estimator, yeah, I would say simply here classical because it's not a good estimate of the variance. Yeah, on average, you underestimate the true variance here. Yeah, but it's simply the same form as in the fixed effects model, that it is 1 over the sum of the WI hat. And you get simply this approximate standard confidence interval in the same way like in the fixed effect model, that you have your estimate from the random effects model plus minus the standard error times the critical value of the standard normal distribution. So let's come to the first example in R. So I have simply here a data set of 8 randomized controlled clinical trials comparing the effectiveness of amlodipine and a placebo on work capacity. So the data situation is as follows. In both groups, we have an information about the sample sizes. We have an information about the sample mean, and we have an information about the sample variance. So the index E for the amlodipine, because it's the experimental group, and the index C for placebo, because it's the control group. Yeah, so, and what we want to know is whether amlodipine is better than placebo. Simple question. So how can we try to answer this question when we look at the results of these 8 different studies? Of course, you have to define an effect size. When you denote by mu E the expected value in the experimental, so the amlodipine group, and mu C in the control group, maybe you are interested simply in the difference of the expected value. I call the difference here delta. Of course, it's easy for you to estimate the difference of the expected values given the data on the slide before. You simply take the difference of the sample means. So it's not really a consistent notation here, but it should simply here that is the mean in the experimental group minus the mean in the control group. And the experimental group and the control group are independent. You may know that the variance of the sample mean is something like sigma square over the sample size, and you can estimate sigma square by the sample variance, so that an estimator of the sample mean, of the variance of the sample mean, is the sample variance divided by the sample size. Yeah, and since the 2 groups are independent, we simply can add the 2 variances. So when you have now your estimate of your effect size, the difference of the normal means, and when you have an estimate of the variances, yeah, you can do the meta-analysis easily in R. So, and I will switch a little bit between the R packages meta and metagen to show you what are the, especially the difference and what you have to, and maybe you can then decide which method package you will use. A lot of meta-analysis methods are really implemented in both of the packages. Yeah. So Meta4 is maybe, I think, the most extensive one. The Meta package is a little bit better for kind of an introduction. So what you have to do is, when you will see the program later, in the R package Meta, you simply have to use a function which is called metagen, simply for metagen, gen here generic. So, and you have to have an estimate of your effect size, and then it's always important what are the arguments in the R function. And for the metagen function, you need here the standard error. So not the variance here, but you have to take the square root of this variance estimator here. Yeah, and with SM summary measure, yeah, in these quotation marks, you can see which kind of effect size maybe you want to do, but it's not important to say it here because you are the one doing the meta-analysis, and you know that it is the difference of the normal means here. So maybe you can ignore the options here. Yeah, but the important thing is that you need a vector of the effect size. Yeah, and here in boldface, yeah, that is the second argument, the vector of the standard errors. Yeah. So, and I have not had enough time to update here my first part. So this is the command which is not valid anymore. It was the decimonial layered estimator as a default in estimating the heterogeneity parameter. The author of the packages has changed the default method, but it's not so important. So what you can do, you can plug in the data, let's say by hand, what I have done here. Yeah, we have the data in the first group. I simply call it here N1. Yeah, then we have the sample, the mean, I call it X1, and then we have the variances, Y1, I call it here. Yeah, and then the second group, yeah, the same with N1, X2, and Y2. So then you can calculate the difference of means by hand, X1 minus X2. You can calculate by hand the variance. It's variance 1 divided by N1 plus variance 2 divided by N2. Yeah, so the good news is that you do not have to do it usually by hand. Yeah, I just want to show it here when you use the Meta-Again function. Yeah, there are other functions in the R packages where it is not necessary to do the calculation here I did before. Yeah, so, and then simply you load your package, what you want to do, library meta. Yeah, and then you want to use the generic inverse variance method with the meta 1. Yeah, and recall that I've told you that you need the vector of the standard errors. Yeah, and you can do the calculation directly when you now use the Meta-Again function. The first argument, DI, are the effect size estimate, and the second one is simply the square root of the variances you have already calculated here. Yeah, so, and MD stands for the mean difference. So that simply means that when you want to have a nice heading in your output, you can give the summary measure here. Yeah, so, and when you print the object, you will get in former times, I would now I have to say this result here. Yeah, so I've meant here command that output is not the current default anymore. But you get the result from the 8 individual studies when you do the calculations. So these are the DIs with the corresponding study-specific confidence intervals. And what is nice here in this package, just for demonstration, is that the author gives you the percentage of the fixed effects and of the weights in the fixed effects and the random effects model. So that simply means that you see what is the impact of each of the study in the total average, weighted average you calculate. And so that simply means that in the first study in the fixed effects approach would get a weight of 21%, whereas in the random effect approach, it only gets 70.5%. And that you have to keep in mind in the when you do meta-analysis, and usually do it in the random effects model. What is the effect that you additionally estimate this heterogeneity parameter? The weights always becomes more equal in the random effects model. Yeah, when you look here, studies with a larger effect in the fixed effect model have a smaller effect or a smaller weight in the random effects model, whereas studies with a small weight in the fixed effect model, here study 4, have a larger effect in the random, have a larger weight in the random effects model. That you, however, have to keep in mind. And what I like in this package here is that at least you get the results for the fixed and the random effects model. In other packages, you only get one result, and you have to switch or calculate or do the calculation twice when you want a fixed and a random effects model. And what you see here, there's a certain difference. The reason is that the testimonial-led estimator, which has been here, is positive. So there is a kind of heterogeneity. There are several other results here. We do not talk about this today. And the test of heterogeneity you find here, that is the Cochrane test I have shown you in the slides before as a test of homogeneity here. Yeah, so the p-value is 9%. So it's at least smaller than 10%. And the recommendation is usually use the random effects model because when you compare the length of the two confidence intervals in the fixed and the random effects model, the random effects model always has a larger, wider confidence interval. And it's known that usually the fixed effect model, that's not really a 95%, it's just an approximation. And it could be that the nominal confidence level of these confidence interval is, when you assume that is 95%, the actual confidence level could be less than 90% or so. So, and just I tried to do the following. I have used, just to show you, the same example now in the current version. I hope you can see it here in my RStudio. There is this, so that's the current version of the meter package now, and the author now call it a common effect and not fixed effect. The results here are not nearly the same because now he changed it also to the restricted maximum likelihood as a default method for estimating the heterogeneity parameter. And when you look here at the estimator, yeah, it's now only or nearly equal to 0. And you see that in this situation, yeah, of course, the weights in the random and in the fixed effect are nearly the same. Yeah, so that's important that you always consider what is given in the R packages. It's sometimes not so easy to follow all the updates in the R packages. Yeah. So an important thing now is that finally you do a kind of a graphical presentation of your meta-analysis results, what you do in a so-called forest plot. Simply what you have to do is to say the forest, and then you plug in the name of the meter object. So in my situation here, the meter object is simply called meta1. Yeah, plug in forest meta1, and that is at least the default output here for the forest plot. And of course, you can make it much nicer. What you have here is that you have the results for the study-specific estimates with the confidence intervals, the information about the weights, and the results for the fixed and the random effects model. And here you get a kind of an impression. What are the individual results when you plug in here, when you present here the confidence intervals, and here you have the results of the meta-analysis. Yeah, so, and the important thing is that you have to learn what are the meaning of the squares here. You see that the squares have different sizes. Yeah, and the size of the square here is connected with the weight. Yeah, so the larger the size here is, so the larger the size here is, the larger is the square here. So that you get an impression which is, let's say, the dominating study, and maybe which is a study with the smallest weight in the meta-analysis. In this example here, it's study 7. Yeah. So let's come back to the little bit theory, to the random effects model. And here's simply a list of the available estimators of the heterogeneity parameter. Yeah, so we have a decimonial-led estimator, Polar-Mundell or Mundell-Polar, and so on. So I have 1, 2, 3, 4, 5, 6, 7, at least 8. Maybe there are some others in an update of the new package of the R packages. I don't know it exactly. Yeah. So, and one other estimator here, I give the solution because it's also some what related to the Cochrane's Q is given this Polar-Mundell estimator that you have a kind of a function given here, and remember that the weights without the head is that you have the true variance here, yeah, and you simply have to find the solution for this equation here. You find this tau square such that the form here on the left-hand side is equal to k minus 1. Yeah, and this solution is then called the Polar-Mundell estimator. And of course, if at tau square equals 0, the function is already larger than k minus 1, you cannot find a solution. Yeah, sorry, then you always find a solution. Yeah, and if it's smaller than k minus 1, yeah, then the is the Polar-Mundell estimator then set to 0, because it's a monotone decreasing function in tau square. Yeah, so that simply means when you are to start, you are already smaller than k minus 1, you cannot find a solution. The question simply now is which heterogeneity estimator one should use. It's a difficult question. There is a kind of general recommendation to use the Polar-Mundell or the restricted maximum likelihood estimator, which is now in the R package meter the default. But generally, it's my recommendation would be that you use different estimators and simply look whether there is an impact on the analysis or not. Yeah, and of course, the result or the question here is that the choice of the heterogeneity estimate affect the statistical inference on the fixed effect. Yeah, the answer simply is yes. We have already seen it. Yeah, when you look at the result here, yeah, when there are some difference between the fixed effects and the random effects model, when we use the decimonial-led estimator, there is a difference. But when you look at the result, or recall the result I've shown you with the restricted maximum likelihood estimator for tau square, where it was equal nearly to 0, then the fixed effect F model is nearly identical to the random effects model. So there will be differences in the analysis in the random effects model depending on the choice of the heterogeneity estimator. This we have already discussed, yeah, and so one of my theoretical contributions to these area of random effects model is the result here. What one can show is that the estimate, the standard error here we have, usually underestimates the true standard error of the random effects estimator. That simply means that the confidence interval here is usually too small. And we have proposed another variance estimator here. So the M, let's say, for modified in 2001, and there is now a little bit by chance, 1 year later in Statistical Medicine, also by Siddiq and Jonkman, the same idea that we proposed in the two papers here, this confidence interval, and with a different standard error, and instead of the standard normal distribution, we have the k-1, a t distribution with k-1 degrees of freedom. So this approach sometimes is also now called the Hartung-Knapp-Siddiq-Jonkman approach. And this is also implemented in the R packages. Yeah, so before I give you an example to normal outcomes, some comments, general comments. So we will use the random effects meta-analysis model. And it's important that you know that it's a very general model we assume here. You can have every effect size, every parameter here you are interested in. We have already seen the mean difference. I've already talked about a little bit about the relative risk for binary data. You can use everything. The assumption is that the estimator is at least approximately normally distributed with an average effect size theta, and the variance then is decomposed in two parts, the heterogeneity parameter and the estimator of the variance of the estimator from the eyes study. If you have tau square equals to 0, this model collapses to the fixed effect model. So we do the analysis conditionally on the observed, let's say, standard error. Of course, we ignore the statistical uncertainty. We usually do it for the standard error, but we also do what we do is we ignore a possible correlation between the estimator and the standard error. And of course, a maximum likelihood estimator, for instance, is not always unbiased. It could also, so it's also important that here, it's a kind of, we just say average effect size, but exactly you do not really know what is the average effect size, even if you do some kind of simulation. And the unknown parameters we have in the random effects model is theta and tau square, and we have to estimate these by the estimates from the individual studies. So a brief overview of the two R packages, just to show you which functions are available, and they have a, let's say, different strategy. We have already seen in the R package meta, this meta-gain function, what is doing generic inverse variance method. You need the estimates plus the standard errors. And it's not necessary to do the calculations in the same way I did for the mean difference. If you have the data like in the amlodipine example, you can also use the meta-con function, and then the function is doing the calculation of the effect sizes and the standard errors for you. The same is done when you have binary outcome data or correlations, single means, single proportions, single incidence rates. So these are, let's say, the first 6, 7 functions you have in this R package, to do meta-analysis in the way I've already shown you. And then there are some other functions available. We have already seen the forest plot. We will also discuss meta-reg and funnel today in this workshop, and meta-bias. In the meta-4 package, it's a little bit different. There is this effect size calculation function, ESCalc, and in a lot of effect sizes, you can do the computation here. It computes the function, the outcome, and the sampling variances, so the square of the standard errors. And that's very important that you distinguish it correctly. In the MECA package, you always need the standard errors, and here you have to use the square of the standard errors. And then there is only one function, rma.uni, where you do the meta-analysis, what I've already shown you. And there are some other functions which you can look at if you are interested in. So, and the important part here is these effect size calculation function, that you can do the calculation for dichotomous variables when you want log relative risk, log odds ratio, or risk difference, for event counts, quantitative covariables, and correlations coefficients, or other measures. And there are a lot of effect sizes calculation implemented in these functions. Yeah, so it's a very useful one. Yeah. So, and maybe before we do a break, I will give you an example for combining meta or results experiments doing meta-analysis with normal means. So just here, a copy from a slide we have already seen. Yeah, we are going to look at the random effects meta-analysis model. Yeah, so what we want to do is we want to estimate an average effect size. Yeah, and we need an estimate of tau square for the heterogeneity parameter. And when you have normal outcomes, I just want to consider here comparative results, experimental group versus control group. And I've already used the notation with mu E and mu C for the mean in the experimental group and the control group. And positive effect sizes, we have already seen that you can use the difference of means. But also you can use the standardized difference of means. That's simply the difference of means divided by a certain standard deviation. The advantage of these measure is that when you have different trials measured with different units, then you have here an effect size, which do not have a dimension, so it's a dimensionless unit. And what I've seen, especially also in agricultural sciences, maybe that you use a ratio of means. Sometimes also I've seen the notional risk ratio here. So simply you could divide your expected value in the experimental group by the expected value in the control group. With the same effect here, that the units will cancel out. It's also called dimensionless effect size. So, and we have the data here for the k-independent studies. Again, with my notation that here now, let's say in the experimental group, we have the sample size, the sample mean and the sample variance, and with the index 2 in the second group. You can simply estimate the ratio by simply considering the ratio of the sample means. And recall, I've already told you when we have some kind of multiplicative effect sizes, the analysis is usually done on the log scale, because then you get a better approximation in finite to the normal distribution, so that you have to calculate the logarithm of this estimator here, and you need an estimator of the variance of the log of this estimator here. And you see that is the result when you estimate it. And you see that the estimator depends not only on the sample variances, it depends also on the sample means. So that simply means that there is a correlation between the logarithm of the log ratio and the variance estimate here. But as I've shown you, I told you on the one slide with my commands, we ignore in meta-analysis simply these correlation. And the correlation is usually not so large. So I've looked a little bit in the literature, so when I prepared some of the slides here, and the reason why I choose now the ratio of means here is simply from the first paper I found from 2002 in agriculture. That's a meta-analysis, and they really say they use the R package Meta4. And I found another paper also. I have nothing to do with this Knapp from southern part of Germany. I do not know him. And they also use the ratio of means in their meta-analysis. But also in some other examples, I have found the standardized mean difference. So maybe that's of interest for you when you do the meta-analysis, yeah, that the ratio of means and the standardized mean difference maybe are two effect sizes which are important for you. So now will he show you the result or show you?
Dr. Knapp,
Yeah.
this slide 30 is extremely important for the workshop attendees from the School of Agriculture and not the agricultural background. This is really very, very important. So now we see applications of meta-analysis in agriculture, right?
Yes.
That's wonderful.
This is true. Bimalda, this is true.
Yes.
This is very important because this shows the real examples of meta-analysis, including fertilization, including cropping systems, biodiversity, and land use.
Yes.
Right.
Yeah.
Thank you, Guido.
Yeah. So it's my first meta-analysis workshop for the agricultural sciences. And the reason is why I haven't shown much more data on this, because I have no idea what soil tillage and fertilization and something else maybe you know what to do. And I just want to show you some kind of, that is also important for you, I've understood. Yeah, so I was very happy when I found at least, I think it's an Italian paper, when I looked at the names here, and they really said that for the meta-analysis, which are done they use the R package metaphor, and I follow simply all the lines. Now what I have done just with another example. So what I've used here as an example from ecology. I also have no idea what is going on there, but there are 102 studies, something with elevated CO2 levels on woody plant mass. So the important thing here now is, for my demonstration in a workshop, is that the data is already available. And I've already told you in the beginning that there is a, let's say, new R package metadat, which contains now the data sets which were in former times included in the metaphor package. So you have to load the package. And the data set I use here is Curtis 1998. That is the example here from the ecology. And when you want to have the information, as usual, when you use R, you make the question mark and then comes the data set and you get the information. Yeah. So what I've done then, simply I've copied the data set in an R object dat and look at the beginning of the first 6. And I've deleted a lot of variables. Just to show you what is important now for the first demonstration. So given here is the following, and that's important. You have the means, now the standard deviations, not the variances, the standard deviations in the experiments, and the sample sizes. In the first group and in the control group. So one group is the elevated CO2 and the other control group is the control group. And I want to show you here to do the analysis when the ratio of normal means is a parameter of interest. So, and the important thing is, I've already shown you the formulas, but it's not necessary that you do the programming. The R packages is doing it for you. What you have to do is simply to use these effect size calculation functions in the package metaphor, and you can do it in this way. You say the measure is the ratio of mean, then you have, and now it's the same notation, the variable names like the option names, that you have the means, the standard deviations, and the sample sizes. And then the same for the second group. And you want to apply it to the object that where the data is. So and when you now compare what happened when you do this was the part before, and then 2 additional variables have been added, yi and vi. And now that's very important to understand what has really happened here. You really say here that it is the ratio of means. But when you look here of the ratio of the means, it's definitely not what's being presented here. It's already done on the log scale. So what you get immediately when you have the multiplicative effect sizes here, Yeah, that is the calculation on the log scale. So that simply means that yi here is the log transformed ratio of means. Yeah, and the vi is the corresponding sample variances. Yeah, when you do the recalculation, so this is now what is called vi in the data set in the R package. Yeah, so that's very, very important that you know what's going on. And that's different in the two R packages, Meta and Meta4. In the Meta4, you directly get the results here on the log scale. Yeah, and when you do the meta-analysis here, yeah, it's simply the RMA.uni function. You can delete the uni RMA is sufficient. Yeah, you here give the effect size estimate. Yeah, plus, and now it's also important, yeah, the corresponding sampling variance. It's not the standard error as in the other package. Here it's the square of the standard error. And here simply I choose the method decimal-layered estimator we have already seen. Yeah. So and then you get the results in the Meta4 package. Yeah. So it's also the estimator here. Yeah. We ignore all the others. Test for heterogeneity is again Cochrane's homogeneity statistic. And then you get the results on the log scale. Yeah, so this is not the estimate here for the ratio of the means, but it's for the log of the ratios of the means. Yeah, so that's important. It gets a standard error, the Z value, P value, and the confidence interval. And that's the standard confidence interval, the approximate standard confidence interval I've shown you. Yeah, so that's important. Yeah, there is not really, yeah. So in the other package, in the meta package, yeah, you sometimes you get some details about the results. Here you do not get the details. You have to really look carefully into the description, what's going on. Yeah, so when you want to transform the results to the original scale, yeah, you have to use the predict function here in the Meta4 package. Yeah, and the important part is here now the first 3 lines. Yeah, we do not talk about PI prediction intervals here. That's not important today. But that is that you get the back transformation to the original scale. You have to say here that as a transformation, you use the exponential function, and then you get the result for the meta-analysis for the ratio of means with the corresponding confidence intervals. Yeah. You can also use the Knapp-Jonkman approach. So I have to drink a little bit. So it's simply the option here, what you have for the test. That is not the classical one. That is the Knapp-Jonkman approach I've shown you. And of course, when you want to see the results on the original scale, I want to either to compare it. Of course, the meta-analysis result is always the same for the estimator. Yeah. And the effect usually in the standard confidence interval is that it is too short. And usually with the Knapp-Jonkman approach, you get a wider confidence interval, and the actual confidence coefficient is usually closer to the nominal one in this approach compared with the standard. And of course, I don't show you here a graphical display of the results because we have too many studies here, namely 102. Yeah, and you cannot display it in a forest plot. Yeah. Alternative analysis in the R package meta. Yeah, here you could use now the meta-con function with the same type here that you use. Now it's the option is here mean SDE. Yeah, so it's always for experimental, and you have to start with the sample sizes, but it's similar to the SCAL function, but it's simply here another version how you can do it. You get simply then the results here that you have the information, 102 studies. Yeah, total sample size here is 1,577. And now very, very, very important. Yeah, so this is the result you immediately get from the meta package. And these are the results back transformed at once to the scale of the ratio of means. The analysis is already done on the log scale. Yeah, so all the results here for the heterogeneity is for the log scales. You see here it's the decimal estimator is 0.0216, and that's the same result you get here in the Meta-4 package. Yeah, and the test of heterogeneity here is also 769. Yeah, and we also have the 769 here. So these results here are also on the log scale, but the author here of the package, yeah, when you get the results here, do the, let's say, back transformation immediately. Yeah, and you get here the results for the common effect and the random effects model on the original scale. Yeah, that's important. And here you get a little bit more information what you have. So maybe that's important. Maybe that's the last slide before the break. Some remarks here on using the 2R packages. Yeah, so first of all, always read carefully the description of the functions. It's very, very important that you plug in the correct information. Yeah, so the meta-analysis for the ratio of means is done on the log scale. Yeah, in the meta package, so you have to transform back the meta-analysis result to the original scale. Yeah, so and note the different strategies for the back transformation I have shown you in the 2R packages. Yeah, in the last package, yeah, you have to do it. The author did it immediately. Yeah, in the other package, you have to use the predict function. Yeah, so if the mean difference or the standardized mean difference are the outcomes, so abbreviated by MD and SMD, then the effect size will be combined on the original scale. So there is no transformation needed or done. Yeah, so that's important. You have to keep in mind. Yeah, so and it's no problem to do it. When you look in the simply in the SCAL function, effect size calculation function, so you have simply to change the name of the measure. Instead of ROM for ratio of means, MD it's for the mean difference, and SMD is for the standardized mean difference, and you can do the meta-analysis along the lines I've already shown here in this way here, yeah, simply with the RMA function in the Meta-4 package. Yeah, and the same holds for the alternative analysis here in the R package. Meta, yeah, SM is here the summary measure. Instead of ROM, yeah, you simply have to say MD or SMD, and you know, when you can get the results for the mean difference or the standardized mean difference. So that would be my first part. Are there any questions, comments?
That has been a great, Dr. Knapp. This has been, should be very clear to all the participants. But I think questions we can take at the end, and we can have a 15 break. We can have 15 minutes break.
Yeah, that would be good. 15
only,
minutes.
Only thing is I can find one question in the chat bot where it is written, can we choose any method of estimation of the heterogeneity as we wish in the R package MetaGen?
No, once again, what estimator you?
Any method of estimation of heterogeneity as we wish in
R
package
sure.
MetaGen.
Yeah. So the slide I've shown you with the names, all the heterogeneity estimators are implemented. Yeah. So that was when I had this slide with simply method equals to DL. That was for Desimony and Laird. When you say REML, it's restricted maximum likelihood. ML, it's a maximum likelihood. HS is Hunter's met. Everything is possible.
Dr. Datta, I hope it is clear. There is another question. Can you please tell me again the inference after doing meta-analysis? This is from Dr. James.
What is
from Ghana? He is from Ghana and he is asking,
okay.
Can you please tell me again the inference after doing meta-analysis? He basically says that he is not clear with the inference.
Maybe I go back to my slides. So that simply means what is the interpretation of these results here? Yeah, I guess. So what we do have here are our significant results. So that simply would mean that when you apply now, let's start here with the random effects model. Yeah, you would get an estimate of 1.2880 with these confidence interval. Yeah, and what we test here is that the effect is 0 or equal to 1 for the ratio of means. And of course, yeah, based on the result here, 1 is not in the confidence interval. Yeah, we would reject the null hypothesis that the two means or the expected values are identical. Yeah, and the p-value is small. And the same holds for the common effect model. Important thing is now simply when you look here at the results, which result do you want to, should you present? Of course, you should use the random effects model here because we have here the test of heterogeneity, and clearly here heterogeneity is present. The p-value is very, very small. That simply would mean that we would reject homogeneity assumption, and you should use the random effects model. So that is one possibility. The other possibility is looking at here at the estimator of the heterogeneity parameter with the corresponding confidence interval. Also 0 is not included in this confidence interval, and that also speaks for using the random effects model. So important thing is just that you have to keep in mind here now, what is the null hypothesis for the ratio of means. Maybe I can go back to the slide with here. For the ratio of means, it means there is no difference if the two expected values are identical. So the null hypothesis would be theta 3 is equal to 1. And in the other cases, it would be when you have the difference of means or the standardized difference of means. There is no difference if these are equal. That would simply mean that theta 1 or theta 2 is equal to 0. And that is the important thing simply you have to keep in mind for the analysis.
Right.
I hope this answers the question.
There are some more questions, but I think we'll take in the second part. Let us break for the 15 minutes, if you agree, Professor Knapp.
Okay, 15 minutes is fine. Thank you.
2004, therefore 2020.
Okay. I think that's a great idea. Thank you. Thank you, Dr. Parsad, for a 15-minute break. Yes, we all need break. Okay.
Okay.
Dr. Parsad, can you hear me? He's
yes,
sir. Yes, sir.
Okay. Rajender.
Yes, sir.
I suggest that sometime in the fall, sometime in the fall, we request my UMBC colleague, Dr. Kifle, who was supposed to be a co-presenter today, but he could not.
Yeah.
He was not here, something else to do. So
Yeah.
I suggested sometime in the fall we bring him back, Dr. Kifle, back to particularly go over the agricultural experiments meta-analysis.
That would be really great.
That particular, that slide 30, there are 4 examples. I'll ask him to read those papers and present to us, including our package, whatever. That would be really helpful for the workshop attendees from the.
That would be really grateful. That will be really great.
Yes, I think we can do that. No, sometime in the fall, I'll check with Dr. Kifle. We can pursue that. Okay, no
we
problem.
shall definitely do that, sir.
Yes. All right.
Okay.
Yeah, in this thing, when it comes to meta-analysis, I am with you all the way, and I'm very pleased to be a part of it. Okay, because it has been. I started working on meta-analysis since the 70s.
Yeah, this is going on as a sumptuous dinner for us, academic dinner.
Like many other topics, SMA has been with me. It's not leaving me anytime soon. Okay, all right, let's take a break. Thank you.
Yeah.
Okay, can we start? Professor Knapp, there are 2 more questions. Can we take those first?
Yes.
The first is minimum number of studies required to perform meta-analysis.
That's a
Good question.
that is a good. I will share the screen.
It's a very good question.
So it depends first where you are working. So when you simply look at the random effects model, so the simple answer is k equals to 2. You need 2 studies, then you can do meta-analysis. And for instance, it's sometimes in Germany we have an institute. Can you hear me? Yes.
Yes.
Sometimes they have really the problem that they should combine the results only from 2 studies. The important thing, of course, is when you only have a few studies, do you get really a good estimator of the heterogeneity parameter? So there is not really a rule of thumb, which now you can apply all the methods starting with k equals to 2. And yeah, so that's a simple answer to the question.
There is one more. This is again with from Dr. Parveen Meher. Whether only different experiments can be combined or the results of different methods can also be combined.
Yeah, so I think when methods means that the 2 different analysis results of the meta-analysis, so I'm not quite sure what methods should mean.
Parveen, are you there?
Yes, sir.
Yeah, you can ask your question yourself.
So, for example, for the same data, we are applying 2 different or 3 different methods. And those 2-3 different methods are providing different results.
Okay, yeah. So I've expected, sure. Then I understand your question. So it would be a kind of, let's say, model averaging or something like that. I've never seen it, to be honest, but I've already thought about it a little bit. Yeah, so given the different results, of their, whether there is also a meta-analysis of meta-analysis may be possible, but I don't know it. But it's a good question.
Thank you, sir.
Yeah, but Guido, I think there is a general approach that for this kind of data, you work out p-values and then combination of p-values, there are several methods.
Sure.
That could be a way out.
That could be a possibility, yeah. But to be honest, so in the application area I worked up to now, I've never seen this idea, to be honest. Yeah. So theoretically, I understand what you propose. Yeah. Sure. Yeah, so it's, for instance, it's important when you look at the, so I've closed my RStudio. Yeah, so when you look at the different results, yeah, here in these amlodipine example, yeah, especially when you use different estimators of the heterogeneity parameter, you can also get different results here. Yeah, so there is a dependence on the estimator of the heterogeneity with respect to the results. Yeah, but on the other hand, I haven't seen any, let's say, controversy results. So that the p-values are most of the time relatively similar. But maybe it's an idea to think about it. Yeah.
I think we can start with this second session.
Yes.
Okay. So it's a little bit about the same like for normal data. I first give you a presentation here for the binary data before I consider two different aspects for the publication bias and the meta-regression. And maybe it was, again, when we do it here, maybe it will also be clear what is the final inference, what we do here in meta-analysis. So now let's consider that we have binary data. So in these studies or trials, you are simply looking at an outcome which is binary, like success or failure. Again, in the experimental group or in the control group. And when you denote by PE the success probability in the experimental group and PC in the control group, possible effect sizes, maybe the risk difference, that is the difference of the success probabilities, you could use as a relative risk, that is the ratio of the probabilities or the odds ratio given the form here. And important thing is that you need the data. I think it was also in the chat a question about the mean and the standard deviation. How do I get? Yeah, so the publication must deliver the information. You must find the information about the data in the published literature. Yeah, so and an ideal situation here for the binary data is that you could extract the data in the 2x2 table. Yeah, when you have the success and failure in experimental and control group, I denoted here simply by ABCD. Yeah, and the total in the experimental group is NE and the control is NC. Yeah, when you have these 2x2 tables, then you can do everything. Yeah, estimating the risk difference, relative risk, or the odds ratio, starting that the you estimate the probabilities by the relative frequencies. A divided by NE in the experimental group, maybe when successive is interest, and C divided by NC in the control group. Yeah. So if you have the situation, maybe like in, recall the environmental tobacco example, where the relative risk was already given, then you have to choose the relative risk as the effect size. So there is a notion here with the two-step meta-analysis and one-step meta-analysis. I'm not so happy with the notion here that it's a two-step meta-analysis, but there are two possible approaches for meta-analysis when all the data you have, or in other words, when the data given in 2x2 tables, and that is available in all the studies. It's always important to see which information do you get from the studies. Yeah, the examples I've showed you, for instance, in the ecology, it was that we have the mean, the standard deviation, and the sample sizes in all the studies. But it could also be maybe for the mean difference that in some of the studies, only directly the mean difference is given and not the mean of the two groups. So it is always, it could be a different data situation. And what I present you here in this workshop today is a certain kind of ideal data situation. So, and when you have the situation that in all the studies, you have 2x2 tables, you can do for the odds ratio 2 different approaches. So the two-step meta-analysis approach, that is generally for all effect sizes possible here. First, you calculate your estimators, whether it's a risk difference, relative risk, or odds ratio, and the sampling variance in each study. Again, for the multiplicative effect sizes, log relative risk and log odds ratio. And then you use the generic inverse variance method. That's the name of the general method, of the generic method I've shown you before the break. But in one-step meta-analysis is simply that you directly use the data of the 2x2 tables. It's a science that you have in this situation individual data and not summary data. And there is a possibility that you can use a little bit a more complex model. So I don't want to talk too much about the formulas in these models. Here I just want to show you how to do the analysis in an example. And that is a classical example, always shown in such kind of workshop, because we will use it, this data set also for the meta regression at the end of today's workshop. So that's an example from medicine, and that we have 13 studies examining the effectiveness of the Bacillus Calmette-Guerin BCG vaccine against tuberculosis. So, and this data set is given again in the R package metadat, and here are given the 13 trials. And what you see here is then the number of the vaccines, whether it was positive or negative, and control positive, negative. So the number of tuberculosis after the vaccine and after in the control group. And there are two other variables here. This applet I will explain later to you will play a role at the end of the study. You have here the information whether it was successful, positive or negative with respect to tuberculosis. Old studies, several authors. And when you look at study number 8, a very, very big study. And Madras, you see that was a study in India. So the largest study you have here in this example from 1980 is from India. And the question now is whether this vaccine is effective against tuberculosis compared to control or not. So, and for demonstrational purposes, I've used the log odds ratio here, simply to show you also the R program for the one-step meta-analysis. So to do the meta-analysis, it's not important that you know exactly what are the variances and how to estimate it. You can do everything in the R package. Again, we do it in meta4, and now we calculate the log odds ratio. You use the scalc function, and the measure is OR for odds ratio. And you have plug into the data what is A, B, C, and D. Treatment positive, treatment negative, control positive, control negative in the data set. And that's all. And then you get the same as before, that in the DAT, you will get the YIs and the VIs, and the YIs will be the log odds ratios, and the VIs the corresponding sample variances. Same principle. So then it's again, when you have a multiplicative effect size, relative risk, or odds ratio, the meta-analysis is done on the log scale. For the risk difference, it's done on the original scale. And then you simply get directly the result and you are done. Yeah, and once again, what's going on here? Yeah, so you get an estimator for tau square. Yeah, now I've used the default one, the restricted maximum likelihood estimator. Yeah, it's 0.3378. Yeah, you get the result here for the heterogeneity. Yeah, as a big heterogeneity given. Yeah, p-value is less than 0.01. And then you have the result here. Yeah, you get a negative estimate. Yeah, for the average odds ratio. Yeah, it's minus 0.7 oh, minus 0.7452. Yeah, with the standard error. Yeah, to calculate the ratio of these. Yeah, with a p-value which is less than 0.0001. Yeah, so it means, so you get a negative result. That simply means given the vaccine, you observe fewer cases of tuberculosis. Yeah, so the result would be here that the vaccine is effective. Yeah, and you get a confidence interval between minus 1.1 and minus 0.4. Yeah, so again with the predict function, yeah, you get a retransformation to the odds ratio. Yeah, you say, and you get an estimate, an overall estimate of 0.4746 with a confidence interval, between 0.32 and 0.68. Yeah, and of course you can do also the Hunter-Knapp-Sieg-Mankian approach here. Yeah, you get a little bit a wider confidence interval. But the clear message is here, 1, so the odds ratio 1 is not in the confidence interval. So there is a difference between the vaccine and the control. The estimate is negative. That means fewer cases of tuberculosis in the vaccine group than compared to the control group. So we have a significant result in favor of the vaccine. So, and when you look at the forest plot here now in the metaphor package, it looks a bit different. The default version, only the confidence intervals, not the weights. And you get here the results directly for the log odds ratio. Again, with the same interpretation here that the larger the squares, the larger the weight of the study in the meta-analysis. And you see here that's a study from India, study 8 has a relatively large weight in the meta-analysis. And for here as a diamond, you see the kind of diamond or whatever you say in English for this, the result of the restricted of the random effects meta-analysis model, clearly showing that the effect is negative, in favor of the vaccine group. And here it would be 0. That is would be the non-effect on the log odds ratio scale. So you can do also the analysis in the R package meter, where you have the function meta bin. There is a little bit another some different options now with event and the sample sizes, but it's easy to calculate it directly. So we have the positive, that are the events which are of interest, and the total sample size in each group is the positive plus the negative. That is what you have to do. And you do the same for the control group. And you say that the summary measure is the odds ratio. And then simply you get the result again with the common effect and the random effects model. And directly here you get again the result for the odds ratio, whereas all the results here for quantifying heterogeneity are on the log odds scale, log odds ratio scale. So, and you get here the same results as we have already discussed with the metaphor package. So, and of course, yeah, whatever you want to do, yeah, you can change. Your summary measure, RR would be for the relative risk, RD for the risk difference. There is a lot of options that all the heterogeneity estimators are available here. Again, you can choose between the classical standard approach and the Hartung-Knapp-Jonkman approach. And there are in both packages still two other methods implemented. I do not want to talk about this today. Yeah, so there are a lot of possibilities what you have to do here for the meta-analysis. Also here, when you look here, there are different methods here for 2x2 tables for the fixed effect model. Yeah, so there is also Mantel-Haensel method. Yeah, but I don't have have not enough time to go into details here. And I'm not quite sure how important binary data is really for the agricultural sciences, because all the meta-analysis I have found here in the 4 articles I've shown you are with.
It is very much important, Professor Knapp.
Yeah, is it important? Okay, but I haven't found a meta-analysis.
Entomological studies.
Okay.
Yeah.
Okay. Yeah. But for instance, here there are other possibilities like the Mantel-Haensel method one could use in the common effect model. Okay. So I just wanted to show you here finally for the binary data, this kind of the one-step meta-analysis that you can also do some more advanced model. It's a hypergeometric model in the R package Meta 4. You need, when you try to do it, you get an information that you have to load an additional package that just for model fitting. I don't know what really is going on in biased earned, but it's needed, for applying this hypergeometric normal model in the RMA.glmm function. And there you can give a model, not of interest, the model, it's a conditional model with an exact likelihood. But I just want to show you that there is additional possibilities to the classical generic inverse variance method I've talked about most of the time today. And the important thing is also that you get here finally in the last line the estimate. Again, negative, recall it's everything on the log scale, and again with confidence intervals, 0 on the log scale is not included here, so that also you can conclude with this analysis here that the vaccination is effective for tuberculosis. So when you want to have the results again back transformed, you have to use the predict function. So and that would be here the result for the hypergeometric normal model. And here it would be the result for the two-step meta-analysis, first calculating the odds ratio in all the studies and then doing the meta-analysis. And what you see here is that the results are quite similar. And also the confidence intervals are nearly at the same width. Here it's a little bit smaller, the confidence interval here. But it's important that you can only use this model here, this hypergeometric model, normal model, when you have the data from in 2x2 tables from all the studies. That is here important. So that for the log odds ratio, that's the only alternative I will show you here. For risk difference and relative risk, I'll always do what I call here the two-step meta-analysis. Only for the odds ratio, is there a good alternative here, and maybe that the one-step meta-analysis may be preferred here. But there is still a problem. What you can have here is that you optimize the likelihood function, and it could be that you will have some convergence problems. It could be it's possible, that you also get the result that something does not converge, and then you simply don't get result in the hypergeometric model. Yeah. So in case convergence problems occurs, yeah, so the two-step meta-analysis is always a good alternative. So that's it for the meta-analysis when you start. And now I will discuss two topics with you, what you have to do after you did first the meta-analysis. And the first one is the publication bias. Important thing is that remember that meta-analysis is often restricted to published studies. Yeah, you don't have any, you do not know how many studies really have been, or experiments have been really conducted for the problem you have. And you have to find the published studies. And of course, there is always a risk of a biased conclusion when there may be, and that's also an assumption, you have non-significant studies and maybe the results of the non-significant studies are not published. And of course, then you cannot use the results because you do not know them. And it could be possible that then the combined effect, whether it's significant or non-significant studies together, when you would have the results, may change the overall conclusion. And usually the publication bias results from ignoring unavailable non-significant studies. And then it really depends on the style. I think that's a sentence here Dr. Bimal Sinha always said, if the meta-analysis of K available studies lead to a non-significant conclusion, yeah, then the issue of publication bias does not arise. Yeah, so now I've learned when you look at adverse events in clinical trials, yeah, it could be the other way around. Yeah, then you have, when you have a meta-analysis and say, oh no, there are no differences between the adverse events. Yeah, then it also publication bias could be a factor in this situation. But usually, Dr. Bimal Sinha is right. Yeah, we only have to worry about publication bias if we have a significant conclusion in publication bias. On the other hand, you find also in the literature the notion of small study effects. That simply means maybe that in the beginning, when you start with your research, yeah, you have to have maybe several small studies with a possible large effect, so that your study, maybe your drug or whatever you have in the agricultural sciences. Yeah, and it could also be that with the methods I will show you, also you can judge whether small studies effects are given or not. Yeah, so the methods are the same, whether small study effects are given or whether publication bias. And
excuse me, Dr. Knapp.
Yeah.
Yeah, I want to make one small comment here. I remember that in one of the international conferences which I attended, I presented a paper on meta-analysis. It was based on only 5 studies. And the participants, they are making a lot of noise. Well, it's been only 5 studies. But this topic, the problem we have at hand, is very important. We are sure that there are many other studies you are not aware of. I said, it's quite possible. Then I said, no, it's good to know that there are other studies. Can you give me some leads? Can you give me some references? And then started whispering this and that. Maybe one here, one in Australia, one in New Zealand, one in Canada, one in Turkey. Just random thoughts. Finally, I was able to get one name in Australia. So I made a phone call. And the person was very surprised that, yes, I did some study a long time back, but it's not very significant. That's why I did not publish. That means non-significant studies, they remain like under hidden, they are unpublished. But then they could have important information also. And then another time, the person was not willing to give me the results at all. Finally, I eventually pestered a few times, and finally I got the results, but it was clear that the results were not out of any actual experiment. He just made up some numbers because he just wanted me to get off his head or back. So you have to be careful when you really look for unpublished studies. It's not very clear whether they are reliable or not. Anyway, go ahead.
Yeah, okay. Yeah, very, very good comment, Dr. Sinha. Yeah, that is also the part, more or less, when you all the participants now remember a little bit the 4 stages we have. I have just briefly discussed with this data collection, especially data extraction. Yeah, so that's always important that maybe when you are from the agricultural sciences, that you are the experts how to judge whether the data are good data, whether they are reliable. Yeah, so as a statistician, sometimes it's not possible to judge it, whether the data are good or
yes,
not.
Good point, very good point.
Yeah. So I just want to give you a simple idea for this file drawer method. To be honest, I've just seen this in the area of psychology and not so in other areas, but it's a simple, I think, simple, nice idea to just get an idea whether really so many non-significant studies really exist. So the idea simply is in the following way. That we have, again, K available studies. We did the meta-analysis and they get a significant result. And what we do is simply, so those Dr. Bikas mentioning combination of p-values. Of course, we could do also here the combination of p-values, and we would reject the null hypothesis. And the question simply is now, does a set of, let's say, K0 unpublished non-significant studies exist, which would have made the rejection of the null hypothesis on the basis of all the studies, K plus K0 studies, impossible. And one possibility to use a combination of p-values is the inverse normal method, to just give a little bit here the ideas. I think we don't have to give too many details. What we simply do is, we transform the p-values with the inverse of the CDF of standard normal distribution, build a combination statistic. And then simply we add studies with null effect. That simply means the p-value, so it's a one-sided testing problem. The p-value would be 0.5, so that the inverse here is equal to 0. And then they can ask how many studies we have to add here, this K0, such that from this rejection here, we will get the result here as a non-rejection. And then you can simply calculate the number by forming these inequality, so that on the left-hand side, we only have this K0. So, and this is easily done in the R package. The so-called Rosenthal method is the inverse normal method I've just briefly introduced to you, and you can use the function FSN, shortly for fail-safe n, in the package metaphor. And a little bit playing around again with these, always stick now to this data.
Excuse me, can you go back, please, just one slide? This is for the workshop participants. So we start with case studies and we compute the p-values, and this is the standard test. And we are assuming that we reject the null hypothesis, so the treatment is significant. We are wondering now, maybe there are many unpublished studies which are non-significant studies. If we had access to them, then the combined thing could have been non-significant. But we are not sure how many are out there. So let's assume this number K0. They are all non-significant studies unknown to us. So we are combining them along with the case studies which are available to us. So total of K plus K0. So what will make things turn around? On the unpublished studies, we have no idea what is the level of significance, non-significance. We are assuming that it is roughly null hypothesis, that is 0. So the p-value will be that's the idea. P-value will be 0, and then we are computing this one. P-value will be 50%. Must be will be 0, and that is how we get the number. This is the Rosenthal idea in the mid-1770s. Very simple idea to get a bound on the number of unpublished non-significance K0. So in applications, we compute this value. Suppose K0 is 500. Suppose. Then we have to have 500 unpublished non-significant studies to defeat the conclusion we have. Instead of being significant, it will be non. But then we wonder, 500, so many, that's a number, Then we have to figure out whether really that many non-significant studies exist or not. Okay, that's the whole idea. Go ahead, Dr. Knapp.
Okay. Yeah. So now you have already got the interpretation for the results here for the example here. Yeah. So you can use simply this FSN function. Yeah. I've already discussed lines before. Yeah. And so the idea simply then is, what is the observed significant level? What is the target significant level? Yeah. So usually it's 5%. Yeah. And as Dr. Bimal Sinha already said, when it's a large number, yeah, I think you do not have to worry about. So in this situation here with the vaccine studies, you would need 607 studies with null effect, yeah, which has not been published. Yeah. And can you believe it that, yeah, really in the world, yeah, you will find 600 unpublished studies? No. Yeah. So in this situation here, you do not have to worry about publication bias. So you can play a little bit around with this target significant level, yeah, whether from this very slow p-value to a p-value of 5%, also you can also go to a p-value only for 1%, yeah, but even the change from the small p-value to a p-value to 1%, yeah, you would need 297 studies with a null effect, yeah, so that you would get a p-value of 1%. Yeah? So in this situation here, don't worry about publication bias. Yeah, so you only have to worry about the publication bias when you would get here a number, maybe when we have this 12 or 13 studies for the vaccine, yeah, and maybe it would be, let's say, 3 or 4 studies, yeah, you only need for changing the result from significant to non-significant. Yeah, maybe then you have to worry about a little bit about publication bias. Yeah, so the classical one also I found in the agriculture paper from 2021 is the use of the funnel plot. And the important thing here is that you have to get an idea about the funnel plot and a formal test for publication bias. And it's just a graphical presentation with a certain idea. And I tried to give you the idea here on the formula, on this slide here with the formula for the confidence interval. And then it's just, let's say, graphical presentation. And it's, of course, always when you look at graphics and you have 10 people, maybe then you have 12 opinions or something like that. So the idea is starting, come on, starting with the simple example here for X bar. When you have a sample mean normally distributed, and think about a confidence interval. So the standard error is the square root of sigma squared divided by n times the critical value of the standard normal distribution. So, and it simply means that the larger n, the smaller the standard error. So that means as a measure of precision, what you have is that when n goes to infinity, yeah, so you would simply have the point x bar. And when n, let's say, goes to 1, yeah, the interval gets wider and wider. And that is what you do then in a funnel plot, that you plot your effect size against a measure of precision. And you can think of different precisions, yeah, and the solution here is that you plot it here as a precision, yeah, the inverse of the standard error. Yeah, that simply means the smaller the standard error, the larger is the precision here. And to put it in a graphic on top, and we'll see it on the y-axis, yeah, so that here again the plot, the standard error here is 0. Sorry, I have to. So you plot your effect size estimates, yeah, again now in these lockouts ratios for the vaccine example, and here the standard error in the way that now on the top here is 0, and yeah, so you decrease the precision to the bottom. And that's simply what is given here in the white area, the idea of these kind of a confidence interval. Yeah, that is more important that you understand. Here at the bottom, when the standard error is 0, yeah, then the overall effect would only have these confidence interval. Yeah, and then when you decrease or increase the standard error, yeah, the interval gets wider. And what the idea of the funnel plot is usually that you see don't see any structure. Usually what we expect is, yeah, when we have studies, let's say also with a small effect, that we have a large standard error, that here are some studies with, again, these large effects, what we also have here, and no studies here. Yeah, but at least here is one study. So the idea is, and let's go back to the slide here, it is a kind of an informal assessment of publication bias by a graphical model. Yeah, if no bias is present, this plot would look like a funnel. This is because there will be a broad spread of points, yeah, for the highly variable small studies. That would mean that you expect here a lot of variability. Due to small sample sizes at the bottom, and decreasing spread at the sample sizes increase with the indication that the publication bias is unlikely to be a factor of the meta-analysis. So the vaccine example is not the best one because we have also a lot of variability with all the different standard errors here. But I hope you a little bit understand. Yeah, one would expect, yeah, a larger variability here when no publication bias is present, yeah, and that the spread decreases when the standard error gets smaller. Yeah, so and when there are maybe in the bottom part here, only studies are here and no studies are here, yeah, or there, yeah, then one maybe expect publication bias. But the important thing is it's just an informal assessment by a graphical model. And I've already told you, when 10 people looking at such a graph, maybe we have 12 different opinions. So an asymmetric funnel plot may indicate a possible publication bias. Yeah, so you can simply do this funnel plot with a typo here. It's not a forest, so you have to change it here. It should be funnel. I have no idea why now here is forest. So maybe it's a copy and paste. Yeah, so the function is not called forest. We have already seen what a forest plot is. It's a funnel plot. Yeah. So, but the important thing is that also you get a kind of test. And there is this Eggers regression test usually used for assessing publication bias by a test. What they do is simply to fit a linear regression model, and it depends. So the dependent variable is the estimator, and the standard error here is used as a kind of an explanatory variable. And what one can think is, when you look at it's a kind of a transformation of the funnel plot idea here, is that you can say the funnel plot is symmetric, that is no publication bias. That's identical, that the slope parameter here is equal to 0. So, and then we could use simply these regression model, estimate the slope parameter, and do the usual test for these test statistic here, so that you would reject the null hypothesis, no publication bias at level alpha if this quantity is larger than the upper critical value of a t-distribution with k-1 degrees of freedom. So, and can use other regression model that is implemented in the R package Meta, that you standardize in a certain sense your estimate, and look at these regression model, and then the null hypothesis of no publication bias is identical to the null hypothesis that the intercept is equal to 0. And you would reject the null hypothesis in this case using these test statistic. These are two different formulations of the same problem, and also they lead to the same conclusions, whether you use this model or this model formulation. So, and what I've done here on the slide is just to show you how you do these Eggers regression test in the two packages we have already discussed, Meta and Meta, and assume that in Meta-4 we already have this R object res. So simply what you have to do is you use the function test for the R object res, and simply say model LM for linear model, because it's a linear regression model. And then you get a regression test for funnel asymmetry. And important thing is here that you get a p-value of R package. When you have a meta object R2, you go to the function meta bias, apply it to the R object, and then simply said meta dot bias equals to Egger. And you get then the same result. So the important part here is that the 60% p-value you find here is also the 60% p-value you find here. Some of the other values are also identical. That's so the estimate of the intercept here with a certain standard error or intercept or confidence interval. You can also look here at the confidence interval. You do not reject the null hypothesis that the intercept is equal to 0 when 0 is included in the confidence intervals. So these are the important things here for the publication bias. And usually you should report the Eggers test for your meta-analysis. You also find this kind of recommendation in the Prisma statement. I've told you in the beginning that these are the preferred, belongs to the preferred items for reporting systematic review, a result of systematic reviews and meta-analysis. So, and of course, there are several other possibilities for publication bias, also for tests. And you can look in the functions, either a rec test or a meta bias in the two different packages. You find more tests for publication bias. Because and maybe I go back to the beginning of the slide here for the idea. Yeah, the important assumption is that you have this, let's say, triangle, white triangle here, is that the estimate you have here on the x-axis and the standard error are stochastically independent. Yeah, so that's the main important assumption you have here. Yeah, that x bar and an estimate of sigma square are stochastically independent. When you have estimates like here for the log odds ratio and the standard error, which are not uncorrelated, yeah, it could be also that under the situation that no publication bias is present, the funnel plot could look a little bit asymmetric. Yeah, and then there are other, let's say, regression tests available that you do not regress on the standard error, but on other measures of precision. Yeah, so you can look in the documentation of the reg test or the meta bias to find other tests. Yeah, but the Egger test is the standard one. Yeah, and it's again like in the generic inverse methods I've already shown you. Yeah, you can apply these Egger tests to all effect sizes you are interested in. And that's the important thing for me today, that you learn the methods you can always apply. So the last topic of today, meta-regression. And that's the reason why I've used, again, this tuberculosis example, because that's the classical example for meta-regression. We have this heterogeneity parameter tau square. And question is sometimes to pool or not to pool. Is it really a good idea to pool all the results, especially if heterogeneity is large? And in case of substantial heterogeneity, whatever it means, substantial between the studies, you should explore possible causes of the heterogeneity. What can you do in meta-analysis when you only have the published data? You can only do it by covariates on the study level. And the important thing now here is also, you need the information about the effect sizes, of the estimates of the effect sizes, the standard errors, and of course, you also need the information for study level covariates from all the studies to do the meta-regression. And it could also be the problem that maybe in one of the studies you do not have the information. And then you also have to do some kind of a sensitivity analysis. On the studies, covariates on the subject level, you can only use when you have individual data. But then I've already told you somewhere in the beginning, when you have individual patient data or the participant data or the individual data in general, you could lose simply linear mixed effects model theory, and we do not have to talk about meta-analysis. But in meta-analysis here now, when you do the meta-regression, you can only use covariates. And that is what we will talk about here, that you have in your model covariates on the standard level. And again, now a little bit the question, how many studies can we use? Should we use for doing the meta-analysis? I've already told you two. But when we fit now a kind of regression model, there is a kind of limitation, maybe also for the Egger test, maybe a short adding to this. You need usually 10 studies to do Egger's test. When you have only a few studies, it's very, very hard to judge whether publication bias is present. And it's the same is here for the meta-regression. You need a sufficient number of studies. So there's a kind of rule of thumb for 10 studies, you can use one covariate. The idea now is to show you how to do the meta-regression. And the important thing, of course, is that you need covariates, yeah, that has a meaningful interpretation for explaining the heterogeneity. Yeah. So, and let's recall here now the normal hierarchical model in my notation. Yeah, what we have done in the first part here is for the meta-analysis. Now I have used here some kind of index MA to theta for meta-analysis and MR for meta-regression. Yeah, that there is a kind of a, let's say, another structural model. Here is always our observational model. Yeah, and now we assume in the random effects meta-analysis model that the theta I, the true study-specific effects, comes from this model. And in the meta-regression part, now we include a covariate here, I denoted by x, y, yeah, and slope parameter beta. Yeah, and also we have two different taus. So the tau square MA for the heterogeneity parameter in the meta-analysis model, and this tau MR square in the meta-regression model. But this parameter is usually called heterogeneity parameter, as you already know. This is called usually the residual heterogeneity parameter. So the random effects model, as we have already seen, looks like this marginally, and the random effects model, meta-regression model, looks like this marginally. Yeah. So, and based now on the data points we have from the different experiments, yeah, we should use the theta MR, the beta, and the tau square. Now we have 3 parameters to estimate, not only 2. Yeah, and again, note that the covariates must have a meaningful interpretation for the question here. And the target, of course, is from a statistical point of view, when we have a good explanation for the heterogeneity, yeah, then our estimator for the residual heterogeneity in the meta-regression model should be much, much smaller than the heterogeneity parameter in the meta-analysis model. Yeah. So, and when we look at the meta-regression model, yeah, what are the objectives? Of course, we want to do the analysis like in the meta-analysis. We want to know whether maybe it's a fixed or random effects meta-regression, maybe that we want to test that these residual heterogeneity parameters equal to 0. Yeah, we want to estimate or give confidence intervals for these parameters, as well as estimates and confidence intervals, yeah, for these theta MR and beta. So the theta MR is then the, let's say, effect size estimate when the covariate is equal to 0. Yeah, and sometimes when you want to have a meaningful interpretation, also instead of x, y as covariate, also you can use xy minus the mean of the x. Yeah, so that you have the interpretation that the theta is then the effect size for the average of the covariates. Yeah, and what we can simply do is extend all the methods from meta-analysis to meta-regression. Yeah, it's always just mixed linear, mixed effects theory. Yeah, can use method of moments, weighted least squares, estimators, and so on. And of course, the model can easily extend to more than covariate, more one covariate. Yeah, simply that you have here a regression approach. Yeah, with also different functions, you can say. Yeah, it must be not a linear regression. It could also be a quadratic one, or whatever could be a good explanation. So, and just one note to the R package now coming. The author of the metaphor package is originally a psychologist. I do not know how you, in agricultural sciences, what you say to the covariates or independent variables. It should be not often an or. In psychology, it's called moderator variables, and that's the reasons why there is an option mods in the R package. So, and again, I will use this example with the India study in number 8. And we have these positive and negatives in the treatments and the controls. And then there is the covariate, briefly called here applet, which is the absolute value of the latitude of the study size. Yeah, so it's just the absolute value because one study was conducted on the southern hemisphere. Yeah, so everything is now put on the northern hemisphere from these studies. And maybe the absolute latitude or value of the latitude may play an important role here for the effect of the tuberculosis vaccination. Yeah, recall, yeah, when you look at the forest plot, that there are different results here. In the India study, there was no effect, but in other studies, yeah, there were larger effects. Yeah, and when you look at the, sorry, confidence intervals, there are really some studies with non-overlapping confidence intervals. And the question would be, is it really a good idea to pool all the results or not? And we can apply the meta regression in the Meta-4 package simply in the way now that you use the applet, the absolute value of the latitude, as a moderator. Yeah, so simply the same in the RMA function. Yeah, we have the vector of our estimates, the sampling variances, and now we add a covariate. Yeah,
Guido,
and then
you would like to take a small break?
No, it's not. I think it's okay, but I'm nearly done. Only 4 or 5 slides. So we get the same result. Now the result here for the residual heterogeneity, it's 0.05. We get also a similar test for heterogeneity based on Cochrane's idea. Yeah, so test of heterogeneity, residual heterogeneity is still significant. Oops. And now we get 2 estimates, an estimate for the intercept and also for the moderator variable here, the absolute latitude. Yeah, and what you see here is that the estimate here is negative. That simply means the farther away you are from the equator, the more effective is the vaccination. Yeah, and this result is significant. And when you want to predict or get the result for the different study site, yeah, you use again the predict function. Yeah, and now you get different results without the transformation first. That here now you get the prediction for the 13 trials with the model, with the meta-regression model, with the confidence, with the standard error, and here the confidence intervals. Yeah, and what you see here is that you again get some significant results here. And for instance, for the India study, yeah, you do not get a significant result, and you only have a small negative value here. Yeah, so no good news. Good news for you in India. So the vaccination does not really work in India, but there is an explanation why it is. So you don't have to worry about tuberculosis. Yeah, when you
Dr. Knapp, I remember that, as I was growing up in Calcutta in the 20s, 30s, 40s, and 50s, it was a very bad. See, it was serious issue, and we are always scared of getting TB.
Okay.
And the vaccines. So I don't know, maybe we are out of that, we grew enough immunity and that's why it's not effective anymore, or?
No. So I will give you an explanation because maybe Kolkata is too far, it's already in the north and not so close as Madras to the equator. So the equator is the important part. Yeah, so there is at least no, and I have a sentence on the explanation here. Yeah, when you use a predict function, again with the back transformation, yeah, you will get the results here. So, and the conclusion here now for the BCG example is the latitude has a significant effect on the effectiveness of the vaccine. the farther away the vaccination is from the equator, the more effective is the vaccine. Yeah, so, and then I only know this kind of biological explanation that people born or living close to the equator have a higher natural immunity against tuberculosis. And that is what I only know about this. Yeah, so when you are living closer to the equator, yeah, then it's maybe it was a change. Yeah, but when you look at the India data, yeah, so the reason is also when I think that's the latest study here from 1980 in Madras. Yeah, and I think there was already the expectation that there is only a few problems with tuberculosis. And that's the reason why you have this big sample sizes. Usually you only need big sample sizes when you only want to detect a small difference. So I think that it may be the explanation. I know that people living closer to the equator have a higher natural immunity against tuberculosis. When you look farther away, yeah, the vaccine is effective. But of course, also you have to look at that there is also a lot of, the first study here, what is it, from 46, yeah, up to 90, 80 in India. Of course, it's also a long period. Maybe it's also a nice example only for showing the meta-regression with a kind of biological explanation. I have no idea whether this biological explanation is okay or not. But on the other hand, from the statistical point of view, yeah, when you look at the heterogeneity estimator and the random effects meta-analysis, yeah, it's 0.3116, and now it's reduced to this value here for the residual heterogeneity. Yeah, so from a statistical point of view, yeah, we have obtained the result that we have a kind of good explanation. Yeah, what I have given here, yeah, that the farther away you are from the equator, the vaccine is more effective. So, and that was the part of what I wanted to talk to you today for this meta-regression workshop. Just a small outlook here for the meta-regression. You can use the model for further application. Of course, I've already said that you can extend the model to more than one covariate. Also, you can think about, what I've already said, a quadratic regression, or whatever it is. Usually, the notion meta-regression is used primarily for explaining heterogeneity between studies. But also what you can do, the techniques, the model, you can use for other application for combining results. Maybe you want to combine results from controlled and uncontrolled studies. In meta-regression, when the covariate just indicates that you have the results only from a controlled or from an uncontrolled study. Yeah, so that simply means not only comparative trials, maybe also have single group trials. Yeah, and also what you can do with the meta-regression part is to do some kind of subgroup analysis. Maybe that your X in the meta-regression gives you an indicator, maybe whether it is a group in the Northern Hemisphere or Southern Hemisphere, or maybe it's in India, in Europe, or in the United States. So you can, and then you also can a little bit more model when you have subgroup analysis, where you assume a common heterogeneity variance in the subgroups, or different heterogeneity variances, and everything is implemented in the R packages, and simply study, the description, the documentation, when you do maybe subgroup analysis, that you can easily do the analysis with some of the options given in these R packages. So, and simply some more on meta-analysis. The first one you have already seen at the beginning. So the book we wrote in 2008, with a lot more of theoretical results. And already Dr. Sinha talked about the other books now, given that there are more books on let's say, also the combination with the R packages. Yeah, so in our book also the last chapter is on R and SAS. The SAS code is still valid, and the R code you can completely ignore. Yeah, so in the last 15 years, yeah, there were so many changes and dynamics that it's not valid. Yeah, so in 2020, yeah, so there was a group and a handbook of meta-analysis. I just want to mention it now that there are some editors given a handbook of meta-analysis, and maybe also you can find something which maybe can be used for the agricultural sciences. So there are a lot of other aspects of meta-analysis, and I do not have time or so in this, let's say 3 hours in total to tell you too many details. So I hope that you have learned at least the basic ideas of meta-analysis. It's important that you know what is the difference between the fixed effect and the random effects model. In most of the situations, the random effects model is the appropriate one, and that you at least have an idea how you can use R packages to perform the meta-analysis on your own. So thank you very much. So that's the end of my presentation.
Thank you, Dr. Knapp. Thank you so much for a wonderful exposure to meta-analysis, following the route from starting from the basics all the way to some of the advanced topics. And I think for the workshop attendees, yes, a lot of applications with theory. You can see not that deep also. Most of the time we can use the standard large sample theory tools, but there are some deep papers, and there's much deep work also on meta-analysis. Papers appeared in the Annals of Statistics, the Journal of the American Statistical Association. Papers appeared in Biometrica. Papers appeared in the Journal of Multivariate Analysis, and so on. So it can be a very deep theoretical topic also for for research scholars. But as well, of course, application also is very important. So we really thank Dr. Knapp for this wonderful exposition to the topic of meta-analysis. Of course, this is only the beginning. You have some idea of what to do and what not to do. But for further reading, there are some references to the handbook and to many other R packages you can use. And so the idea is, whenever you think that there is a need to combine results from various experiments, of course, the experiments, the way we are looking at it here, the experiments are independent, and they're all trying to respond to the same cause, the same, so that combination or data synthesis or research findings, putting them together, it makes sense. Otherwise, if the different experiments are addressing different problems, then there's no meta-analysis. So the whole idea is of meta-analysis, independent experiments, all addressing the same issue. We have the findings from different experiments, so either hypothesis or estimation or whatever. Then there's how do I efficiently, in a valid way, combine the results of the experiment? That is the whole topic of statistical meta-analysis. And the presentation by Dr. Knapp is certainly a very nice exposure and a good explanation with some insights also. So, Guido, on behalf of all of us, I thank you, and of course, over to Dr. Parsad. Because if you want to add something, please feel free.
Yes, I have one important point to tell. So, in the process of making the presentation, it was very elaborate as much as possible and quite relevant for this group, because we had thought of 2 workshops, and one is, of course, the meta-analysis part. And when this idea came to us, I immediately thought of my twin brother Bimal, because I knew about the book and I heard him and also Guido in several places. So we had no difficulty in identifying the speaker. And I told Rajender Parsad about this group, and immediately we went ahead. Now, in making the presentation, at one point of time, Guido made an observation that if there are 10 people, 12 opinions will be formed. And I was wondering, how is that possible? And within seconds, I could see the solution. Only thing you need is one assumption. You assume that in that group of 10 people, both Bimal and Bikas are present. And they will be the first to make opinions. And after the 10th person, they will beg for revising their opinion. And then they will go for adding 2 more opinions. That is how, even though there are 10 people, 12 opinions will be formed. That is very interesting. Okay. They are always there to modify the opinions. Okay.
Right.
Back to Rajender now.
Next, one second. So I want to also mention that Dr. Knapp is not an alien to India. He has been all over India many times over the years, with me, without me, with my brother, without my brother. He has been, in fact, he was invited in Vellore to offer a workshop on meta-analysis, probably spanning over 3 days for the medical doctors there. It's probably before the pandemic, maybe about 7-8 years back. And he has been to northeastern part of the country, of India, Assam and so on, some areas there. Of course, he has been to Calcutta, and Symposium. And he has been, Guido and I, we flew together to so many places for the globe to offer jointly this workshop on meta-analysis. Of course, my part will be very minimum, just the introduction, and I'll introduce him, and he'll take the last share. So, thank you, Guido. Thank you so much for being so supportive of this topic, and also for being with me for so many years. And I'm very, very pleased to know that whenever I request something, and Dr. Knapp, please do it, and he always ready to do it. Thank you. Thank you.
You know, Dr. Sinha, you're always welcome.
Thank you. Over to Dr. Parsad.
Thank you, Vimalda. We all agree that we had a wonderful, outstanding, very elaborate, a difficult topic in simple terms, elaborated to this group who has started some work on meta-analysis, but still at the beginning stage. This exposition, this sumptuous dinner to India community provided by Professor Knapp is really going to be really helpful, nutritious for all other academics endeavors to come. I would also like the participants to give a big hand, big clap to Professor Knapp, Professor Bimal Sinha, and Bikas for arranging this nice workshop for all of us. And I will also request everyone to switch on their videos so that 1 or 2 screenshots can be taken as memory of this event. And this is Professor Knapp. This is only a beginning. We will be there with you and Professor Bimal and Bikas again for more insights. Over to Ajit for a formal vote of thanks.
Thank you, sir. Thank you very much. So, friends, it's my proud pleasure to extend a vote of thanks. We are extremely grateful to the co-chairs, Professor Bikas Sinha ji and Professor Bimal Sinha ji, for very smooth conduct of the workshop. Thank you very much, sir, for spending your valuable time and your able guidance for conducting this workshop. We are profusely thankful to the speaker of today's session, Dr. Guido Knapp, for his meticulous efforts in explaining the concepts and applications in a very lucid and simple manner. Sir, you explained everything, basic concepts, applications, data, R, interpretation, everything, whatnot. Thank you very much, sir, for this excellent presentation, sir. And we are thankful to our director, Dr. Rajender Parsad ji, who has been a source of inspiration and guidance for organizing this workshop. Sir, we had with us very senior colleagues today, Professor Padam Singh, Dr. V.K. Bhatia, Dr. V.B.S. Sodia. So thank you very much, sir, for being with us in this evening. And last but not the least, I would like to thank all the colleagues, all the students who were there, who enjoyed this excellent talk. Thank you very much, sir. Thank you, Maryland.
Thank you so much,
Thank you.
And Vikas,
Thank you too.
thank you so much for this sumptuous dinner.
Okay.
Yep.
Thank you. And
Thank
good
you.
night.
Okay, Guido.
Bye
Bye-bye.
bye. Bye
Guido,
bye.
thank you. Okay. Bye bye.
Ajit, we can close the meeting.
Right, sir. Right, sir.